Good afternoon, everybody. Welcome to Ellensburg, Washington, USA. On a very chilly Wednesday afternoon. I mean, it's 26 degrees, but it's one of those where the air is cold and it's trapped in our valley. Freezing fog day after day, no sign of the sun. Wah, wah, wah. So walking across campus is kind of a trudging experience, and it's midterm time here on campus, and so it's just kind of a bunch of walking zombies walking around here. But I've got energy reserved just for you, and you're going to get my best effort here in the next hour plus. And I hope that you enjoy this program on the Coast Mountain Batholith. Coast Mountains Batholith. So the local time, by now, after that few sentences there, is about 1:49, let's call it, p.m., and we will begin this session in about 10 minutes from now, or more or less, at the top of the hour, at 2 p.m. Pacific time. So these Wednesday afternoon sessions are late for our European viewers, typically. People on the other side of the planet, for some of those folks, the time zone works better. So if you've been curious why we switch it up, why isn't it always 9 o'clock in the morning? There's a bunch of reasons, but that's one of them. So let me grab my coffee mug, say hi to folks, make sure we're 5 by 5, etc. 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 However you're supposed to say it. And before you know what? Before I forget, let me get that volume down. We'll say hi to some, oh boy, got 300 people. Damn, son. I'll stay live for a second. We are 5 by 5 in Webb Lake, Wisconsin, Selma, Oregon, Red Deer, Alberta, Bangor, Maine, Nashville, Tennessee, Crescent City, California, Bremerton, Washington. Take a breath, boy. Jackson, Louisiana, Falls City, Washington, Dayton, Ohio, Paddock Lake, Wisconsin, Seattle, Washington, heard of it, Las Vegas, Nevada, Guayaquil, Hawaii, Tasmania, that's Hobart, Tasmania, for those keeping score at home. Oakland, California, Bend, Oregon. I'm still live, I'm just watching things stroll by like a maniac. Crewe, England, Bastrop, Texas, Grand Junction, Colorado, East Lansing, Michigan, Wanaka, New Zealand, Rockmart, Georgia, Cologne, Germany, Lake Ozark, Missouri. Another Hobart, Tasmania? Come on, Teza. Are you hanging out with Bryce? You guys have to be, right? Blodgett, Oregon. Steve, there it is again. Steveston. Come on, Steve, is that it? Steveson? Wait a minute. You're Steve from Steveston, British Columbia? Are you the mayor or something? There it is again. Okay. All right. I just got a jolt of electricity being here with you. Like, again, it's just kind of dreary, like everywhere today. I'm grading the midterms, and it's not a good scene in my office with all scores. Oh, my God. So this is uplifting for me, and hopefully for you, too, in a way. Slowing down in the chat now. Getting echo in the sound, says David. Are we doing okay? Let me ask again. Are we 5 by 5? I mean, most of us are veterans now, so I'm pretty confident now with the audio. Let me double check, though. Truly 5 by 5, we don't have any issues? I'm maxed? Yeah, okay. Good, thanks. Yep, so the echo's on your end, whoever that was. Okay, Catherine, Northern Territory, Australia. Wonderful. Love the distant lands, as always. Skagit County. Dominican Republic, that's a first, Mitchell. I think that's a first. That's cool. I mean, Norley's just trying to get to Panama. She's, yeah, itchybooch.com. Pamela says, yes. Oh, Stevenson, a beautiful wharf seaside town near the BC-Washington border. Oh, really? Stevenson, not Steveston? Okay, don't get hung up on it, boy. Yeah, for your British Columbia viewers, talking about your province. Don't get too excited. I don't know much. Jim Munger called it the CPC. Yeah, we'll talk about that, Frank. Yeah, there's different ways to. Yeah, okay. You're stealing my thunder, Frank. Come on. Okay, let me. The guest is going to start wondering what's going on here. Let me email her. Thank you for being here. Honestly, I'm uplifted by your presence. I'm not kidding. Concentrate, boy. Okay. The guest has been emailed back to you. We have 450 or so folks still rolling in. Lady Edith in Warsaw, Poland. No, Lady Elin is saying Warsaw, Poland. Wow. So whoever's from Warsaw, welcome. I don't think I'll scroll back. So if I haven't said hi yet, just retype if you wouldn't mind. It's scrolling nice and slow now for the moment. Kansas City, Missouri. Elaine's in Tucson. Spending spring break in Tucson with Liz. Murrumbina, Melbourne. Ian, hello. Hurrah. Huzzah. Alberta Gary in the house. Finland. Different person from Finland. Pinehurst, North Carolina. Phoenix, Arizona. Perth, Australia. Gatineau, Quebec. Vienna, Austria. Yeah, these distant lands are fun, and many of you are regulars. Laufenburg, Germany. Camino Island, that's in Washington. Playas del Coco. Is the guest Ivana? No, I haven't followed through on Ivana yet. I'll have to figure that out. Anchorage, Alaska. Denise in Tokyo. It's 7 a.m. in Tokyo. Hi, Denise. Menominee, Wisconsin. Plenty of Badgers here. Odense, Denmark. Angola, New York. Still don't have our guest in the green room, so let me start worrying about that for a second. Hang on, let me check my inbox. Frick, Dave Rogers was in there as soon as I hit send. I don't know how he did that last time. That was record time. We are the world. Thank you, Dixie Doodles. Ogden, Utah. Honey Greg. Hey, Greg, thanks for the honey. Used it over the weekend. Liz and I were out for a walk, and we came in here, and I showed her the big bread head. She said, let's take it home. Let's eat it and dip it in honey from that guy in Tennessee. So we did. So breadhead is no more. Breadhead is in my system. We enjoyed it. Thank you. Here's to you, Binman's Bakery. Okay, we still don't have a guest, so now I'm starting to officially, this is a first. What is my plan if I don't? So I have her text number. I'm going to text her quick. iPad's working, but I see the battery's running down in the laptop, so I'm going to be itchy to get to the laptop sooner than later before I lose the... Keep waiting for this new laptop to show up with multiple ports. Kim's in Lahaitis Golf Resort. Wow, that sounds great. Murder, She Wrote. Rockland, California. Breadhead would have been a cool pizza. Yeah, I agree, Lethal Lee. 563 watching. I'm about to take my watch off. I think some of you veteran viewers know what that means. Hello, McKinney, Texas. San Diego, California. We've got about 3 minutes or so, and Bath, UK, Derbyshire, UK, Prosser, Washington, that's Charles. Eugene, Oregon, thank you, Martin, thank you. San Jose, California. It's cold even in Miami, Florida, reports Clint, coast to coast. Hey, Clint. You would hate it out here right now, man. It is winter, winter, winter. Paul wants a hot mic. You're getting, well, yeah, the mic is hot at the moment. Where is our guest? I don't get it. Texted her and emailed her. Could be a first. Could be improvising for an hour. Bob and Squim, hello. Tim in Bellingham, Washington. 40 degrees C for the next week in Perth. What's that in Fahrenheit, Andrew? That's up there, though, right? Yeah, I usually try to watch the Australian Open a little bit, just because I'm itching for sun. Okay. So we don't have Breadhead today. Thanks again to Vinmans. I don't have any thank yous necessarily. I do want to remind everybody that we are continuing. This is our show today and our show Saturday. We'll be still talking about magma, January magma. But then when we turn the clock to February, we will be done focusing on magma. We'll still bring it up. But okay, I got a text from her now. Hang on. Okay. She did get the link by email. She's running a few minutes late. No big deal. She said she'll be with us momentarily. Okay, that makes me feel better. Andrew says 104 degrees Fahrenheit for the next week in your town in, was it Australia? All right, well, that doesn't sound like fun to me. I got, you know, the extremes are what, we're all like that probably, right? Okay. Okay, well, I've got 1 minute or so. Would you mind giving me a chance to get my head focused now that I know that the guest will be joining us momentarily? Thank you for joining us today. Hope that you enjoy this session on the Coast Mountains Batholith. We'll start in 1 minute. Hot mic. Hot Michael P. Eddy. Okay. Starting with the series reset. Don't make that too long, but that needs to be done. Frame the discussion of today. Talk about your limited background. Use the handouts. Go to the iPad early because I think it's functional and we don't know how long it's going to be functional. You can do that. Don't forget the iPad early. You show the papers, yeah, you'll do that. You can do it that way. Then you go to the chalkboard. Right, you can do that. And get to the guest because you don't know nothing. You do not know nothing. You know nothing. You can do it. There's nothing wrong with your approach. You can do it. Good afternoon, class. Our session begins right now. We are focused today on British Columbia geology, not a strength of mine. British Columbia is not that far away from Ellensburg, Washington, but for many reasons that have been talked about in the past, I don't know a whole lot. So I will be asking some rather rookie questions of our guest, who knows a fair amount. There are 3 separate papers that are waiting for you. We'll go to those in the iPad in just a second. But I think the first thing I want to do is kind of reset the series and remind all of us, including myself, what I was saying early on in the alphabet. You know, we started this A to Z series called That Crazy Eocene. We started that series back in mid-November, and I was laying out a whole bunch of questions and I was kind of brainstorming. I think these are things that I want to investigate, but I'm not sure how much emphasis I will have on each of these features. I know that they're tied to the docking of Silesia, I was saying to myself, but I don't really know exactly how I'm going to lay out the alphabet. And that's still true. That's still true. We're not going that much further in the alphabet, right? We're getting close to the end of the alphabet. But I do want to reset by saying two things. And I haven't rewatched that first show called Goals back in November, session A, in other words, in this series. But I'm pretty sure I was saying a couple of main things. One, I don't know exactly how I'm going to lay this out, and I want to allow myself the freedom to explore things that interest me, that surprise me as we go through the letters. And so, yes, I blame Basil for getting me more interested than I thought that I would in the Cretaceous, in these Plutons and in these terrain stories going back 100+ million years ago. That was a surprise to me. So I know this is a series called The Crazy Eocene, but we've been doing just as much pre-Eocene as we've been doing in the Eocene. So I'm just letting you know that I had that freedom to begin with. I am following the Cretaceous storylines a little bit more than I thought that I would. And last show with the Idaho batholith and the Dave Rogers show, we were talking about severe thrust belts and that sort of thing. We're going to be back in the Cretaceous again today, and if you've peeked at these papers from our guest, you'll see that it's mostly pre-Eocene discussion topics. But that feeds into the other thing that I want to kind of reset our minds and make sure, basically to reassure you if you're starting to feel like we are clearly off the tracks. Like we're off the rails, baby. This guy never talks about the North Cascades, and he's never in the Eocene. What is this guy's deal? I want my money back. Maybe that's what you're saying. Well, I don't remember any money being exchanged, first of all. But second of all, I want to remind you that back in session A and B, I was sharing with you my strategy. My personal strategy. Everybody's got a different approach, but my personal strategy, if there's a complicated area, and the North Cascades in northern Washington is for sure a complicated area, my strategy is to leave. It's like when I was teaching a field class down in Eastern California, which I've shared with many of you. Did that for 20 years. And I could just predict every year which students would go into these complicated areas and just kind of lose their minds and just totally just collapse, basically, and in some cases truly start crying because they couldn't figure it out. My general advice when I would kind of, gently kind of go and visit that mapping pair and they're just absolutely distraught and they have no strategy at all to understand this complicated area, I would just say, it's okay, we can learn this together, it's fine. But I'm going to encourage you to leave this area right now. And they'd be confused. And I would say, you're going to have to map this complicated area in this mapping area, but you're only going to be able to understand that complicated area if you leave. You go up on that ridge. Now, you listen to me, I'm your teacher now. I know that ridge is simple. I know that ridge over there is straightforward or well-behaved. Those are phrases I would use regularly. And after you map the 3 or 4 ridges surrounding this godforsaken swamp, which is incredibly complicated, after you do that mapping elsewhere and you have some themes or some storylines or some relationships or at least some lines on your map, then you can come back into this complicated area and actually make a few connections. You can make progress. So if you're confused about what I'm saying right now, I'm trying to say this. I'm learning about the North Cascades by not being in the North Cascades. Has it dawned on you? Idaho last time. We're freaking Lower Mantle before that. And today, we're up in British Columbia. But I'm learning what I can and then bringing these concepts, these storylines, these themes, these details to the North Cascades. And I have a strong feeling that some of them are going to pay dividends for us. And next week, a week from today, we will be with Stacia Gordon, a member of the Dream Team. Finally, you'll get a chance to meet her. And we will be in the North Cascades. I don't know if we'll be there for good for the rest of the alphabet, but both shows next week will be in the North Cascades, and I will be using much of what I learned today and some of these other shows. He goes to the iPad, hopefully. Splodam. Let's do this before I lose power on the laptop. It's been a while since we've looked at the schedule. There we are, session S with Robinson Cecil. Very much looking forward to visiting with her. And yes, if you're a nervous type, she is in the green room now, so we're good. She's even muted right now. Okay. Wonderful. And we're going to Montana on Saturday. Same concept. Learning some things in preparation for going to the North Cascades. There's the rest of the alphabet, and I think I just let the cat out of the bag that a week from today, February 2nd, Groundhog's Day, we have Stacia Gordon from University of Nevada, Reno, helping us look at the crystalline core of the North Cascades. I mention that because that I probably will come up a little bit in today's conversation with our guest. What else do I have for you here? Oh, yeah. No, not ready for that yet. Let's go to the personal shrine, otherwise known as nickzentner.com. And you know how to get to our papers for our series here. We click on the word Eocene. Have you done this before? Have you been doing this all along? I don't know if you have or not. Maybe that's too much detail for you, but I know some of you have been doing it at least. And so I have 3 papers by our guest today, Robinson Cecil from Los Angeles, California. And she's got a paper that just came out last year, 2021, and then you can see she's been at this. These are my titles, of course, just generically, Coast Mountains Batholith. But this is our first crack, so let me do this one from 10 years ago. Co-authored with George Garrels, possibly her thesis advisor, not sure, University of Arizona. And here's our first look. Are you kidding me? Look at this. In red is the Coast Mountains Batholith. And you're like, I don't know where I am. Well, this is Vancouver Island, Jerome Lessman country. So inland from Vancouver Island, British Columbia, we're going to follow this red, this Coast Mountains Batholith, otherwise known as the Coast Plutonic Complex, otherwise known as the Coast Belt. We're going to find this batholith today, Bella Coola, Kitimat, Prince Rupert, Ketchikan. We're from frickin' Alaska, Petersburg, Juneau. We're going north of Juneau. We're still following this batholith. Are you aware of the incredible size and volume of this batholith? I'm not sure I was totally fully aware of it until really reading and thinking in the last 48 hours with these great papers. Get back, boy. Get back. Get back. Get back. Get back. Get back to where you once belonged. I don't know how to do it this way. Sorry about that. Old guy move. Let me show you a couple other things waiting for you. Here's the paper that came out last year. Uh-oh, Mantle. I got questions, Robinson. Mantle. I didn't expect to have the first word of a scientific paper article be Mantle, tied to a huge batholith in British Columbia. So we'll get there. Notice in one of these figures, she has pink the Coast Mountains Batholith. Maybe we'll just say CMB the rest of today, if I can do that in my head. She's got the CMB, of course, going all the way up from Skagit, Alaska, down, heading down towards Vancouver, BC, and then she's got it stopping at the border. We're about leading to the first major point of my portion of this. If you're new to us, I talk for about 30 minutes, more or less, and then we go to the guest. So if you're waiting for the guest, it's going to be coming in just a bit. Get off of that. Yeah, I want to leave the iPad momentarily. So let's just get a little taste. We were looking at this. Yeah, now's what I want to do. Come on, let's keep going. This is from the new paper by Robinson, and I'm going to be discussing on the chalkboards in just a second what the green is all about. So let's enlarge here. So here she has the batholith. You know the batholith. I'll just say batholith the rest of today. the batholith, the Coast Mountains batholith, is all this pink. So instead of red now, it's pink. The purple is a bunch of metamorphic rock that we'll be talking about with Stacia Gordon a week from today. Not up here, but metamorphic rock in Washington. But I really want to emphasize the position of this Coast Mountains batholith with relation to the green on one side and the blue on the other side. Some of you know where I'm headed, but for the rest, let's just use that be a little sampler. And I think Robinson, our guest today, is most proficient with the southern portion of this CMB. So in other words, she's not, it's a huge batholith, so we're not going to expect her to be telling us a bunch of details from Alaska. I don't know, maybe she was up there too, but she's been doing these transects. And all this data is coming pretty much from Vancouver Island and then working inland. I'm curious about the site selection here and the kind of campaign style that appears to be happening. But notice we have some thrust faults. Again, my chalkboard work will hopefully help us remember the role of the thrust faults, at least in my simple brain. What else have I got for you? Oh, I love this. Again, I'm just taking advantage of the iPad while I've got it, and then I'm going to do some things on the chalkboard. Let's slow down for just a second. This is a cross-section. This is a side view of, let's just say, we're taking a transect through this batholith, the Coast Mountains batholith, the CMB. West is on the left, east is on the right. What's the yellow? Stickinia, which is part of the intermontane superterranes. Oh my God, we got to go back a year ago now when we were talking about these different exotic terrains. That was a surprise to me. I didn't know that some of this work with this batholith was going to kind of spill into a discussion of these exotic terrains that we really haven't been thinking about in more than a year, but we're going to have to dust off some of that today. So yellow is a portion of the intermontane superterrane that accreted 170 million years ago. Green is Alexander, which is Rangelia and friends. In other words, the insular superterrane. We've been talking about quite a bit this winter. Purple, I'm not familiar with the Banks Island, but look at all these blobs. Our focal point are these individual plutons, and if it has not dawned on you yet, if you're a rookie with thinking about geology, a batholith, I didn't get around to saying this last time, I'll say it now. A batholith is just a bunch of plutons together. That's it. It's just a size thing. So the concept of a pluton, the concept of a batholith, same thing. It's a bunch of magma that cooled slowly underground. But if we've got all these individual plutons acting as a unit, that's what we're calling a batholith. And this, again, jumping the gun a little bit with our chalkboard work, but just wanted to lay this out. Let's just look at this for a second. This is Robinson helping us see the entire Coast Mountains batholith in British Columbia. Colors here are ages and millions of years. So we're stretching from almost 170 million years ago until 45 million years ago. That's quite a range. A much wider age range than we have in the North Cascades, correct? But a big major, redundant, a major point from today is that there's these frickin' magmatic flare ups again. That's what I'm about to do on the chalkboard, but we've got 1, 2, 3, 4 distinct flare-ups of magma. It is not the old way of looking at these batholith, which is just, I think even Rogers said it last time. Rogers is just like, the Idaho batholith is just one continuous, magma factory without a whole lot of interruption. I think we now have the definition from geochemists like Robinson today. I think we have the definition now to realize it's not a steady factory, it's not a steady magma factory, but instead we have these individual episodes that need an explanation, and I'm not sure we have it yet. What she is also showing us, and I'm going to save this probably till we get to her, but she's also showing us a distance in kilometers inland from, let's just say, the coast. I'm not really sure what 0 is, but let's just say the coast of British Columbia. So she's making a big point in the text more than once that as we get younger with our magmatic flare-ups in British Columbia, in this huge batholith, we're eating our way inland. Pause for dramatic effect. I didn't freeze there. I just paused for dramatic effect. Marshmallow head in the corner paused. It just happened. Why are we encroaching further and further inland with these magma bodies? We don't really have that in the North Cascades, I don't think, the way that I view it currently. And then this is another thing I'm going to touch on before we go to Robinson. I'm sorry, I got to ask it. Are we sure all these magmas are from subduction? And the obvious reaction from most everybody, including probably Robinson, is of course. But you know where we've been lately with Carr and Siglock and others, with a westward subduction out in the middle of the ocean, or at least entertaining the possibility of this thing called slab failure. So that's the last thing I do on the iPad, because I happen to have those animations queued up for us. So I will, when we talk to Robinson, talk about a little bit at least. She might shut me down and say, I don't have the data to go back and forth with you on this. But this is our Cartoonist Geology 101 view of a subduction zone, and sure enough, we are generating magma much further inland. Now, before I forget it, and since Robinson's listening to us right now, I don't get why we're talking about Mantle in this story. If it's really a subduction story, and I think that's the centerpiece of Robinson's papers, there's a geochemical signature of Mantle generated melts. And I guess I'm missing something at the 101 level. I didn't realize this was a Mantle story. So we'll get into that. To me, the Mantle thing is much easier to visualize with this very different tectonic model, which I'm not in love with, but you recall that we were talking about slab failure as a model for some melts where we break a hole, or we roll back, or we tear, or we break a subducting plate due to some major collisions at the surface. And to me, this is a much more obvious and simple way to get Mantle to surge. Remember Jeff Tepper and the rollback in the Eocene. I'm wondering if that slab break and slab rollback has any possible parallels going back more than 100 million years ago. Probably not, but just thinking out loud. Yeah, we don't need it again. So when we view these beautiful photos in the North Cascades, let's blow it up for everybody. There you go, Gary. When we view this in the North Cascades and we see these plutons in these different skylines, of course I picked a photo that doesn't have many plutons of the right age. Dumb. I'm thinking about these different models the entire time. That's where I am currently. If I have a Pluton, big or small, huge batholith or small kind of bite-sized Pluton, I think up until this winter I just naturally thought subduction. And I think most people just kind of like an instinctive thing. Pluton, subduction. Pluton, subduction. And I'm just starting to think about some of these Plutons of different ages and chemistries, and I'm just wondering out loud in a childlike way, are we sure everything's subduction? And if it is subduction, are we sure it's eastward subduction? Okay, he gets rid of the iPad. I hope the phone doesn't freeze. Cross your fingers, please. We had problems last time. Still here. Okay. Pick up the pace, boy. It's 2:20 here. 10, maybe 15 minutes, and then we go to our guest. You're still here as well. Good. All right. So I think by now this is self-explanatory. This alphabet series is in full go. We are in the zone. This thing is almost operating by itself at this point. At least it feels like it to me. So I don't have to start with scratch with you in other words. Today's topic. North Cascades, Dream Team, next week, Washington. Idaho Batholith, last show, most recent show, Dave Rogers, Idaho State. To me, we've got, not to me, the grant proposal that I'm part of talks about 3 distinctly different ages of magmatic flare-ups in the North Cascades. And I have hit this pretty hard that it looks like there's a compressional tectonic regime in the most basic sense, or possibly a oblique collision where we have transpression. But the point is, we're not extending the crust. It doesn't appear when we generate these huge magmatic flare-ups between 96 and 87 million years ago in the North Cascades of Washington. That's where we're going next week, 78 to 60. And then in pink, that is different. That is the Eocene. That is pulling the crust apart, or transtension at least. And we're generating all sorts of precious metals as well in the Eocene in the North Cascades. I'm putting these circles on top of each other because they are invading each other. I have an ask. Haven't done this in a long time, but I'm going to ask it. I need help with an analogy. I don't want to spend 10 minutes on this, but can you think of something, whether it's food or something else, where you have a liquid rising and then solidifying, weight, then a younger batch of liquids rising up through the stuff that just solidified. In other words, blotches coming up through that same place. Cool those off. Can be food, can be something else. I don't know, something in an ironworks foundry. I don't know. Something that everybody knows, though. And then can we have that third batch, the youngest flare-up of this liquid, this hot liquid? Again, it has to eat its way up through the same general region, in this case the North Cascades, and then we solidify those guys. So when we hike through the mountains of the North Cascades, to the untrained eye, I guess it looks like a bunch of granite, but to the geologists, they know this is not only a ridge full of granite, but there's 3 different generations or ages of granites kind of coalescing. Not mixing, but like have invaded each other. Oh, I'm stuck on ice cream, but ice cream doesn't really work. So I need something there. Thank you for that, now or later. But did you remember from our last show, Idaho didn't have that. There were 4 distinctly different magmatic fluxes in Idaho, part of the Idaho batholith, but there was a geographic trend. I'm not going to bother with the handouts again. But I'll point out that this was near Boise. This was in central Idaho, like the River of No Return. This was up towards the Bitterroots on the Idaho-Montana border. We're going to go back to this and visit on Saturday in Montana, look more at these batholiths of this age. And then it was only here in the Eocene that the blotches just started showing up everywhere. But that was different than here. There was some sort of sweep or some sort of geographic distribution of the oldest to the youngest in Idaho. No sense of it, but they weren't all invading each other in one central location. Well, I've shown the same thing here because this is real. From the work by Robinson Cecil, our guest today, and many others, first of all, don't you notice that our ages are far older than anything we have in the North Cascades? These are plutonic rock ages. We're not talking about metamorphic rocks or thrust faults or anything else. This is just in the Coast Mountains batholith. It's not all the same age. It's not a continuous magma factory, even though that probably was taught as recently as 10 years ago. We now have the age and chemistry distinction to see that there are 4 distinctly different magmatic fluxes in British Columbia in this mammothly sized, terrible, Coast Mountains batholith. I'll let the numbers speak for themselves. I think it's only the recent stuff that's an extensional story. In other words, our pink, our Eocene magmas are showing up even in the Coast Range the Coast Mountains batholith. But there is another one of these age patterns, and we just saw it with the graph from one of the papers. We're going coast to the interior as we get younger. Why? South to north, generally. West to east, generally. Don't have it here. There's a bunch of ways to answer that. Here's one way, just real quickly, and then we're going to the guest. Yeah, we're going to the guest. I don't know if we're going to go here in our discussion. You know that I don't rehearse things with the guest. I met Robinson for the first time yesterday, briefly, just to test the technology. Very pleasant person. I'm sure you'll enjoy her. So she doesn't really know where I'm headed with some of this stuff. But if we go back to thinking, in the old days, from a year ago when we had different exotic terrains that we were learning, I purposely left off the Plutons. The Coast Mountains Batholith is not on this frickin' thing. I wanted to just talk about this fruitcake or this quilt of all these exotic terrains. I'll narrate since it pertains to today. Dark blue, royal blue is Quinellia. Grello is Cache Creek. Light blue, Dodger blue is Stickinia. Orange is Rangelia. Yellow is Alexander. The frickin' Tanana, whatever. You know? So I wanted to avoid the batholiths a year ago because they just muddy up the picture, and that's the point of this thing here. Our talk today is on this enormous batholith, which is hundreds of individual plutons of different ages. You just saw the age range with 4 distinctly different magmatic flare-ups. But it has totally wiped out a boundary that we care deeply about. This is the intermontane superterrane that added 170 million years ago, roughly. That's Quinellia, Cache Creek, and Stickinia. So Cache Creek in France, remember? Docked against old North America in the passive margin 170 million years ago. I've told this story a million times, but I have ignored this batholith because it hides most of the important parts of our story. And I'll cut to our guest who has been looking carefully at the geochemistry within this batholith, I think, to help delineate where this boundary is. That's one of the things she's doing. Like I've just dashed this line in. I have no idea what that line is. Remember, Daryl Cowan says most of the Coast Mountains batholith is Rangelia. That's Rangelia and friends being the insular. Remember, that's the thing that Karin wants fixed out in the middle of the Pacific. So I guess Daryl wants this line way the hell over here between intermontane and insular. I think Cecil and co-authors are maybe wanting to move this line back over here a little bit. And you're like, who cares? Well, here's why you should care. I'm fired up now. In case you're still in that lazy boy and you're like, this guy's doing it again. He's doing another one of these shows and he's not talking about the North Cascades. Well, here's a dirty little secret. Angry suddenly, I don't know why. Most geologists view the North Cascades as part of the Coast Mountains batholith. Now, it didn't show that way in Robinson's map from, I guess, the most recent paper, but let me show you why the North Cascades are viewed as the southern tip of this Coast Mountains batholith. So here's intermontane superterrane, insular superterrane, huge batholith that has eaten its way up through this boundary. That's what I'm showing in pink. That's the Coast Mountains batholith, correct? Now I got scissors. Why? Oh my God, we're going Ellensburg to Skagway, Alaska. That's the size of this thing? Yeah, Mount Stewart's part of it. And you're like, well, no, I don't think it is. I don't think it is. This is you talking now. This is you still talking until I can find the right diagram. Come on, baby. Come on, baby. Where is it? There it is. Washington at the bottom of this map. Look at that Coast Mountains batholith, otherwise known as the Coast Plutonic Complex, all the way up to Alaska. Sitting in precisely the wrong place for us to see the boundary and the relationships between the insular and the intermontane. But I'm trying now to help you see why the North Cascades are part of this huge magma welt. This is from last winter. We were looking a little bit at another huge batholith in Baja, another huge batholith in California, and then here we go. Look at that. There's a fault on the Washington side called the Straight Creek Fault, on the BC side called the Fraser Fault. There's 100 kilometers of offset of the Coast Plutonic Complex. And what is this thing on the east side? It's the North Cascades, baby. This little thing is the North Cascades. We need to restore the Straight Creek Fault to see that when we go to the North Cascades, really for the first time, I guess, next Wednesday, we're going to make sure mentally to restore that strike-slip fault to see that the North Cascades is a perfect continuation pre-50 million years ago. So I owe it to you to actually do it. So what I'm saying is, we had an intact Kilbasa, we had an intact batholith until 50 million years ago. And what happened? Now Silesia is too big for the map. What happened is the docking of Silesia 50 million years ago, obliquely from the southwest to the northeast, dock it 50 million years ago, that's Silesia, right? And the timing of the docking of Silesia does what? It creates the Straight Creek Fault. Can he do it backwards, ladies and gentlemen? Creates the Straight Creek / Fraser Fault. Doesn't go this far north, but just play with me. And in between 50 and 35 million years ago, the entire batholith, except for the North Cascades, have been shifted north 20 feet at a time, with a total of 100 kilometers of offset, 60 miles of offset. 50 million years ago, today. The North Cascades are the southern tip of the Coast Mountains batholith. So there. We are in the North Cascades. Because we're part, the Coast Mountains batholith is right over there with Mount Stewart, if we restore the Straight Creek Fault. Okay. 236, thank you for your patience. Robinson, we're coming to you. We have 860 watching. Looks like we are functional. And I forgot my fancy headphones, so we're back to plugging in properly. Power on the laptop. This is all feeling just right. And let's go to Los Angeles, California. Hello, Robinson.
Hello, how are you, Nick?
I'm doing great. Thank you for joining us. Thank you for playing along with this like we didn't know each other. You got this email from me a couple of weeks ago, and you're like, what is this about?
You bet. This is fun.
Well, you've had a busy day, I'm sure, and looks like you're home right now, so that's terrific. We're going to just make hay while the sun shines here. At least probably sun shines down there. I don't know.
The sun is always shining here, Nick.
Ah.
It's LA.
Good. So
we pray for rain down here.
What is the official name of your school? Is it California State University of Northridge?
Correct. California
Okay.
State University, Northridge. We
Okay.
abbreviate it CSUN.
Got it. And you've been there how long?
About 10 years now.
Okay. So that 2011 paper so I shared 3 of those papers. So was that your PhD dissertation, that 2011 paper?
Actually, no. That was from work I did as a postdoc at Arizona. So I was at Arizona for a long time. I did a master's there, and then I stayed and did a PhD. And then I stayed and did a short postdoc with George Garrels. And that's how I got introduced to the Coast Mountains. I was actually developing techniques for measuring hafnium isotopes, and he said, hey, why don't we try applying them to plutons in the Coast Mountains?
Wow.
And so that was my first kind of dipping my toes into the Coast Mountains. And I don't know that I know a whole lot more now than I did then, maybe a little bit more.
Well, can you give us a feeling for the size, first of all? I'm saying Ellensburg to Skagway, Alaska, but how do you try to communicate to whoever about what you're trying to deal with and the size of this thing?
Yeah, I thought you did a really good job of kind of making that point for me, that the Coast Mountains is really the largest exposed batholith on Earth. I mean, the only thing that kind of rivals it might be the active Andean arc in South America today. Maybe if we could fast forward 50 million years and have the exposed roots of the Andes, it might be kind of similar.
Oh, yeah.
But it's huge, 1,200 kilometers long by about 200 kilometers wide. So the nature of our work there is a lot more exploratory than it is in Western North America, where we're really starting to pick apart problems in more detail. We're still doing kind of, in some ways, reconnaissance level work in the Coast Mountains.
Yeah. Well, speaking of that, so you've kind of stuck to this, I don't know if we break it into thirds or something, you've stuck in the south more or less?
Yeah, we've been working, I would say kind of in the southern third, maybe the southern half of the batholith, depending on where you want to cut it off.
Right.
Although this summer I was up in Southeast Alaska, so I'm starting to move north and go different places. I saw somebody wrote in the chat that they used to live in Ketchikan, and I was just in Ketchikan myself, and that is Coast Mountain batholith there.
Wow.
Okay.
So you, not to belabor this part of the story too much, but so Garrels says, hey, I think we ought to head up to a portion, and you did kind of a transect using the methodology that you were working with geochemically. How did you select that transect?
Yeah, well, I actually didn't go to the Coast Mountains before 2011. So I just worked on a box of rocks. He and his collaborators, most of whom were at the University of Arizona, including my PhD advisor, Mihai Ducea, had a big 5-year continental dynamics project funded. It's like this big kind of interdisciplinary resource from the National Science Foundation that gives big money. Anyway, they were working in the Coast Mountains and had collected, just hundreds of rocks. And so I just kind of started looking at the data that existed and what subset of those rocks would be best to target for our initial hafnium experiments. But that then launched into new proposals. And so George and I ended up writing new proposals together and continuing our work.
So my only real exposure to your world so far is Michael Eddy at Purdue University, where he appears to be kind of equal parts field geologist, where he's out collecting these samples personally, and then he's built this lab at Purdue to do this detailed geochronology. Are you doing the same sort of thing as far as you're out in the field and then you've got your lab built at Northridge?
Yep. I wish I was spending equal amounts of time in the field as I was in the lab, but that's never the case.
Right.
But yes, I'm doing field work and usually in the summers, and then lab work kind of all the time, around the clock. So yeah, I would say similar to Mike Eddy.
So you've been up there multiple summers, let's just say, and are you? How logistically are you getting across that batholith? Are you following a fjord, or are you along a highway and just busting off outcrops, or what's the process of deciding where you're going to go and then how you're collecting what you need to collect?
Yeah, it's a huge challenge. You showed one of my maps that had the sampling locations, and you can see that in the Western batholith, they make these discrete lines, and that's because they were all collected by boat along these glacial inlets, these fjords.
Oh, wow.
And then as you get to the east, they kind of create a more scattershot map pattern. And that's because all of those were collected spot-wise with helicopter support. So there are no roads anywhere, at least in the southern batholith where we've been working. Once you go farther north, it's actually more accessible. The mountains are a little bit lower, they're less glaciated, and there's more road access. So like there's an entire road that goes all the way from Prince Rupert in the west to Terrace in the east that follows the Skeena River. And you can access the entire width of the batholith there by road. But once you go south of the Prince Rupert latitude, you're stuck on boats and helicopters. So it's logistically very challenging and it costs a lot of money. So that's, I think, why there aren't more people tromping around in the coast mountains.
Right. Well, I hope you're continuing, or are you moving on to some other project that's not this topic?
No, I'm continuing. I have projects in Southern California, so I always like to keep one foot in kind of Western North America and have local projects so that I can engage more students here from Northridge. But I'm continuing to work and write proposals to do stuff in the Coast Mountains, and I'm hoping to be back up there this summer, as a matter of fact.
Oh, good.
Yeah.
And you have grad students, or are they undergrads that are working with you, or both?
Grads and master's level students.
Okay.
Yes. So we are just we are master's only granting. And then the UC, the University of California system, is the PhD arm of the public school system in California.
That's cool. I mean, I don't think I've heard of that before. That's neat. So you're training these students with your lab, and then you're also going out with them every summer in the field?
Yep, trying to, yep.
Well, can you tell I'm stalling a little bit? I don't know if I want to go into the geochem or not here. I mean, I truly don't understand the chemistry that Mike Eddy is using to get these incredibly highly precise dates, and I don't have any hopes of grasping your laboratory techniques, but you must have practice communicating some of the isotopes that you work with and what you're trying to solve. Like, are you trying to get you're playing between models about why these magmatic fluxes are happening? If that's true, how are the isotopes helping refine the model ideas?
Yes, that is true. Fundamentally, that is what the problem we were trying to solve. So the question is, if subduction is ongoing for 100, 150 million years, like we believe it was in the case of the Coast Mountains, we had this long-lived Paleo-Pacific or Farallon plate that was subducting beneath Western North America. So that's happening more or less continuously, yet magmatism, as preserved in the batholith, is highly discontinuous. So we have these periods that we call flare ups, where there's huge volumes of magma being intruded into the crust, and then there are these periods that we call lulls, where there's relatively little. And so there's a whole group of us that are trying to understand that. What's controlling flare ups and lulls? Why do the flare ups happen? And so we've been asking devising a number of experiments that we could use to target that. And one of the things that we're using are isotopes. And what the isotopes answer for us is the amount of existing continental crust that is recycled into the magma during the genesis of these plutons. So the isotopes, hafnium and oxygen isotopes and some other isotopic systems, are basically acting like fingerprints. So if we see, for example, negative excursions in the hafnium isotopic numbers, if they become more negative during flare-up events, or if the oxygen isotopes become more positive during flare-up events, that might tell us that there is a greater degree of crustal recycling that's happening during melting. So we're trying to track, physically and chemically, what is happening through time during these flare-up events. Is it all just brand new stuff coming out of the mantle, which was blowing your mind, he said?
Yes.
Or is it, mostly remelting of older pre-existing rocks?
And where are you on that? I mean, I know it's complicated and there's so much granitic rock or tonalitic rock, maybe what you're dealing with. 10 years ago, did you have a different idea than you do now as far as how much is mantle versus how much is kind of native North American crust that's being recycled, as you say?
Yes, totally. So when I started doing this, I was working or thinking about these problems. I was working mostly in the Sierra Nevada, which has a similar record. So long-lived subduction, but magmatic episodicity. So flare ups and lulls. And my PhD advisor was actually, is credited with being one of the first people to publish about this extensively and to address this issue of magmatic episodicity. So I was kind of raised on that, thinking about that and thinking about it from the perspective of the Sierra Nevada. And there we actually do see these temporal changes in the isotope signatures that track with the flare-ups. And so therefore, this kind of prevailing model came to take hold that basically the idea behind this model is that during a flare-up event, you're stuffing old continental crust down into the subarc kind of hot zone, the melt zone where the magmas are being created. And that's triggering, and that material that you're stuffing down, it's fertile. So it's actually going to cause, higher volume melting to occur. And so then you get this big flare-up event. And through various processes that I won't explain, it's able to repeat itself over and over. But basically, this model is a way of relating what was observed in the Sierra Nevada batholith, a way of relating that greater crustal influence that happens kind of in lockstep temporally with these big flare-up events. And the punchline from the coast mountains is that we don't see that.
You don't? Okay. So that was, by the way, what school was that and who was your advisor again?
Mihai Ducea, University of Arizona.
Arizona, okay.
Yep.
And so that's where you kind of cut your teeth on some of this, the
Yep.
Sierras, or the
Yep.
Sierra Nevadas. And is that still the view in the Sierras, that we're cramming that stuff down and getting those isotopic signatures?
Oh, great question. I don't know. If you were to survey 10 people working on Sierra Nevada batholithic rocks right now, what would they say about that? Most of that community has kind of moved on to different questions. But the data, they are what they are. There's no denying that during the big flare-up events, so the big event in the Sierra Nevadas in the late Cretaceous, mid to late Cretaceous, and all of the isotopic signatures have these really distinctive trends toward greater incorporation of continental crust. So that's undeniable. Now, whether or not you think it's reasonable that continental crust was being stuffed kind of down long distances from the east in these big, thrust sheets, I don't know if everybody believes that still, but it's kind of an undeniable aspect of the Sierra Nevada. And we expected to see that in the coast mountains.
Yeah. One more thing with the Sierra. So shoving from the east, did you say, or shoving from the west?
Shoving from the east was kind of the initial, from the kind of interior, older part of the continental North America. So you need old rocks because you need that to satisfy some of the isotopes.
Yeah.
And you need those rocks to be juicy. So they have to have minerals that contain water such that they can be dehydrated upon stuffage down into the lower crust.
Oh my God, you are
melting.
You are doing me a great favor here. I mean, I'm sure stuffage is not in that igneous petrology textbook, but
it's a highly technical term.
That's perfect. Thank you. So we're finally up to BC, and 10 years ago, you're kind of like, okay, maybe the same thing. Maybe the east shoving and the stuffage and all that. And at what point, or was it a very gradual change that you started seeing that this was a kind of a different animal?
I think it was it was not gradual. There was a moment. I was sitting in a lab at the University of Wisconsin collecting oxygen isotope data. And I was very excited to run. There were a few samples that I wanted to look at because they came from plutons that were emplaced during one of, what we had already documented to be the largest flare-up period. And there was some hint in the hafnium isotopes that maybe there was a little bit more continental crust being incorporated into those rocks. But the oxygen isotopes that were that the zircons were recording were showing nothing but mantle-like signatures. In fact, the whole week that I spent in that lab collecting data, we never saw a value that deviated from a mantle-like value for any of our rocks anywhere at any time period. So just incredibly unchanging.
And this is the biggest flare up of the 4?
Yeah, I mean, we looked at all 4 episodes. So we selected rocks that were in place during those 4 episodes, and none of them showed any distinctive trait, none of them had a whiff of continental involvement.
So, but you still like subduction. Can we jump to the fun part where you're trying to well, I don't know, it's all fun, but I mean, so why are we getting mantle swimming into this area, or what should I visualize for why mantle would even be sniffing, as you say, to this coast mountains? I'm getting excited now. I'm stumbling all over the place. We're generating all these.
Going.
Yeah, we're generating all these magmas, and why is the mantle even within arm's reach of this system?
Okay, yeah, you were bringing up those questions earlier, and I got really excited, and I thought, I'll break out my new colored pencils and I'll draw a picture.
Oh,
I started drawing.
Oh, I like you. I like you.
And then I realized this is actually much better illustrated in my published figure. But anyway, this is a picture that I made, and basically the intention behind it is to show you that the mantle is everything. So that's where all melting starts in every subduction zone system. So when the downgoing slab gets deep enough, it starts to dehydrate and dewater, and that causes flux melting in the mantle wedge on top of it. So in essence, all melting at subduction zones is going to start with these, partial melts of mantle. But we know, because, we pick up granites and tonalites and things from around these batholiths, if you melt the mantle, you make peridotite. You make a really mafic rock type. Yeah. So something has to happen. And most people believe that those really mafic mantle melts end up ponding at the base of the crust or in the upper mantle lithosphere. And they create kind of this mushy mafic mantle zone that's hot. And that actually is kind of like the engine room for remelts or additional melting of the lower crust and or some of these basaltic underplates. So you can basically generate, so it's a 2-stage process that allows you to fractionate enough to get to, silica contents that make a tonalite or something like that. Mm-hmm. But it's essentially just a 2-stage melting of stuff that's coming directly from the mantle. So in other words, you're not incorporating either through assimilation, you're not incorporating or recycling the crust in order to generate those more fractionated, more felsic melts.
So what, so you're not a Cascades volcanologist necessarily, but
No.
Like in the Andes or the Cascades, so there's the same mantle at work in those 2 active subduction zones?
Yeah, absolutely. The thing about the Cascades and the Andes is that you're really only seeing the uppermost crustal level, right? And so there's going to be a depth-dependent change in the magmatic rocks.
Yeah.
And so as you get to higher and higher crustal levels, including all the way to the surface where you're looking at volcanics, there's a greater chance, especially in these continental arcs where the crust is very thick, that you're going to encounter plutons that have, in fact, interacted with or assimilated crustal material. But at middle to lower crustal depths, maybe not. Mm-hmm. So it's really important to think 3-dimensionally and think about where in the crustal column you're sampling from. And in our case, we're sampling from kind of the middle crust.
Mid.
Yeah.
And next week we'll be with Stacia, and she's in metamorphic rocks, but that's mid as well, or maybe even low. I don't know how familiar you are with her work in North Cascades, but I mean, I'm just starting to think about this which level in the crust are we? And I'm sure you're aware that there's all this stuff coming way to the surface during the Eocene, at least in the North Cascades. Is there some of that signature up with you as well, that things are popping out of the ground quickly?
Where I'm working, no, but there is a place in the Coast Mountains called the Central Gneiss Complex that would be fairly analogous to the North Cascades crystalline core, where you have the exhumation of these deeper rocks that include, paragneises, so metamorphic sedimentary rocks, and meta-igneous rocks that record a much more complex history. And since this is an Eocene series, I'll just say that, I'm particularly interested in the timing of the exhumation of those rocks. So it happens late in the history of the batholith, probably in Eocene time, and is associated with a big magmatic surge. So there's, probably the most volumetric magmatic surge in the Coast Mountain batholith is happening in Eocene time. Especially
the biggest flare up?
Yep.
Wow.
Interestingly, that's not the case in the southernmost part by Vancouver.
Oh, I see.
But to the north, yes, there's huge volumes of magma that are intruded then.
So if you wouldn't mind going back for a second, so where you've worked, you don't have the metamorphic kind of crystalline core complement thing, and in your plutons, you do not see that rapid rise, or you do in your rocks?
We don't have the extensional tectonism in my region that has exhumed those rocks. They could be there. But the Central Gneiss Complex is somewhat unusual in that, there are big normal faults that have clearly exhumed the Central Gneiss Complex.
Okay.
And so, one of my big questions going forward, and something I'd like to work on in the future, is, are the Eocene magmas that are contemporaneous with that, are they associated with an extensional event? And to what you considered a dumb question before, and it's not dumb at all, are all of these magmas subduction related? Well, maybe that latest stage, the Eocene magmas that are associated with this extensional event, maybe they're not. Maybe they're not kind of bona fide subduction related products.
Well, I'm having a blast. It's 3:00. I got a couple more for you, and then if you're up for it, we'll do some live questions as well. I can't hold it. I guess you've seen enough of this to know that I'm hoping to do a whole nother Baja BC alphabet series next winter. I couldn't.
Ooh, oh boy.
And we don't have to go here in a big way. I was well behaved. It was a full hour before I brought this up. But there is paleomag, I guess, in the entire batholith. Please correct me, to say that if you're a Baja BC person, you're working with Mexican plutons. And they're up there now, but we're not. Even if you're not a Baja BC person, your plutons were down by us. You were south of Ellensburg, I think, right? If you restore all these strike slip faults.
Yeah. So
I don't know if it matters, but I mean, it's an element of this, and does that factor in at all with your work?
It does. So you can't ignore it. And, it does and it doesn't matter. To some extent, I would say it doesn't matter, because a lot of the questions we've been trying to answer are kind of process related, petrologic in nature.
Right.
Why do batholiths fundamentally have this episodic quality? So, where geographically or paleogeographically that's happening is not super important. Also, the transform systems that would have to be doing these translations are roughly parallel to the tectonic grain of the Coast Mountain Batholith. So they're not going to necessarily chop it up. In fact, there's not a lot of evidence in the age trends of the batholith and things like that to suggest that there are these like big discontinuities that we could interpret as faults that might be responsible for those movements. That's not to say that I'm opposed to believing that they could have happened.
Right.
But then there's the timing issue. So when did the timing occur, and which of these magmatic episodes would have been, pre or post docking of these terrains? Which model do you prefer? What distances do you prefer? I mean, there's a million things to juggle.
Yeah.
My brain is not agile enough to
mine either
hold them all at once.
Right.
And so I've been conveniently ignoring a lot of the paleogeographic stuff and just focusing, like I said, on the batholith. But it is critical. You can't ignore it.
Well, it makes perfect sense. I got two more then. So I assume you view the North Cascades as an extension of your Pluton story where you are. That's not a radical thing to say, right? That we're going to restore this batholith and have
that's not radical. I do think they're almost certainly related. I don't, I'm actually just starting to think more about the Straight Creek and Fraser faults and are they actually the same fault, and what is their role in displacing the Cascades and the CMB? These are things that I'm just now starting to think about.
Yeah. But the fact that what I'm leading to, I guess, is in the North Cascades, we don't have anything older than 100 million years old.
Right.
And is that, if we restore this, are we doing one of your transects where we're older than 100 and then we're getting younger by the time you get to us? Or what are your thoughts on this age sweep from the coast towards the inland areas?
Oh, it's a great question. It's something that I've talked with my colleagues Margie Russmore and Bob Miller about. If we were to restore it and then just kind of recalculate the flux or recalculate the arc migration trends, do they look like what we would, do some of the spatial anomalies go away? Can some of it just be explained by displacement of the southernmost batholith from the North Cascades? We don't have the answers to that yet, but it's definitely something to think about. It doesn't solve kind of the missing Eocene problem in the southernmost part of the arc. Why that part kind of seems to shut off.
Where you are?
No, south of me. So
south
Vancouver,
of you.
Yeah.
Okay.
So, and in the North Cascades, there's not as much.
Well, it's all relative, I guess. I mean, we have some Eocene Plutons in the North Cascades, and of course I'm very interested in those, but volumes maybe nothing close to the Eocene volumes you're talking about up in your neighborhood. I think that if that's the biggest flux in the Eocene where you are, then yes, ours is probably a drop in the bucket compared to those.
So I know you probably want to stop talking to me here in a minute, Nick, but since you brought it up, I want to show your audience one thing. Can I do that?
Oh, please. I don't want to stop talking to you, by the way, just for the record. So, we practiced sharing a screen yesterday. We'll give it the old college
I only
try.
have one picture to share you, to show you.
Great.
It's a photograph. Can you see that?
I'm going to bring it in. I can see it. Let's bring it in. Ooh.
So this picture, the only reason why I wanted to share it is, so it's a picture that I took out the helicopter window flying out one season. And every single rock, every single outcrop that you see in this photo is the same Pluton. So this is all mapped and it's Eocene in age.
Oh my God.
It's called the Tiedemann Pluton. And so this gives you a sense, and it's totally homogeneous. You could pick up a chunk of it in the foreground or in at the far background of this picture is still Tiedemann Pluton. And it's incredibly homogeneous. And so this is nothing really, my guess, and I haven't worked in Washington, so this is my hunch, just based on map relations, that there's nothing really of this scale in the Eocene in Washington.
Oh, you're right. You're totally right. Yeah, I mean that a picture's worth 1,000 words. What is the Maybe you don't have a high precision date on it. What's the number that comes to mind for that Pluton?
Oh, I was really hoping you would
boy.
ask me that because
We'll just call
I'm going to get it. Hang on.
We'll call it Eocene. That's fine.
I
That's
really
fine.
wanted to get that right. Okay, I want to say 47, but I could be wrong.
I believe it. That's
It's
what we'll go with.
47 plus or minus, not a few million years.
Right. Well, thank you for sharing that. That does help. Yes, we don't have that scale for sure. And so I'll be thinking hard about our smaller Eocene Plutons. Then we cross the Fraser Fault, and you're saying there's not much at all Eocene-wise, and then we approach your neighborhood, and the things are gargantuan.
Yeah, correct.
Okay. So you might be going in that direction. Is that what I'm hearing you say? You might be leaving some of the Cretaceous in your future work? Are you that intrigued, or is it just kind of an afterthought thinking about these Eocene magmas?
I have plans to continue working on kind of the Cretaceous part of the batholith.
Okay.
That's not going away.
Yeah.
But in my thinking kind of regionally, large scale and over large time periods, I've become increasingly interested in the Eocene, in part because of some of what you've highlighted in your series. It's a really interesting time, especially in the Pacific Northwest, which is genetically linked to the southern coast mountain batholith. And basically just trying to think a little bit outside the box here. Why is it that there are all these like anomalies spatially in terms of the Eocene intrusive rocks? We have them some places, not others. Are they always associated with extensional tectonism or not? Why or why not? Are there any other kind of gneiss complexes like what has been seen in the central part of the batholith?
Yeah.
Is this more, have we just not found them, or is that just a special place? How does that relate to the magnetism? What is happening in the kind of regional plate tectonic picture? Is there, you've probably discussed resurrection plate, and there's a lot of things that are happening then.
Yeah.
The coast mountains shuts down. It becomes completely inactive at about the timing of Tiedemann Pluton emplacement. And then the Crean-Charlotte transform system begins.
Yeah.
So, and the timing of the magmatic pulse and the fundamental change to the plate margin overlaps. So are they, to the best that we can resolve them, of course.
Yeah.
So, are they actually subduction related? I don't know. I have a lot of questions about that.
Exciting. Very exciting. You gotta love it. Okay, it's time for involving our viewers. Thank you, viewers, for waiting a little extra. Boy, I really enjoyed that, Robinson. Thank you. Boy, you are really good. Okay, get your caps locks ready, and I don't know if can you see some of these, Robinson?
I can.
Okay.
Yes, I can.
So I'll pick and choose, but if something catches your eye, please jump on it. And they're all saying nice things. Let's see now. I'm live. We got Crazy Ronnie. Okay, you never know what Crazy Ronnie's going to say. Crazy Ronnie says, what was going on at the surface directly above these locations during these flare-ups? Good job.
Oh, gosh. Great question.
All right.
Presumably, there would have been volcanism happening at the surface at the time of intrusion of these magmatic bodies. We know that there is a record of that. So there are like bentonites, which are like the kind of weathered tufts-like things that are found in the foreland that got blown, eastward a long way. So we have some record of that, but unlike in the Sierra Nevada, for example, where we have, we have the big four-arc basin sitting right next to it that is today California's Great Valley, and that is kind of like the living record of the Sierra Nevada volcanic arc. Right. All of that is offshore in the coast mountains, so we don't necessarily have that whole record exposed. So it's very difficult, with the exception of some places, to actually put your hand on the volcanic rocks that are associated with the coast mountains. All we really have is that kind of underground plumbing system currently exposed today.
Sure. What kind of silica content are common in your rocks? Are they kind of tied to more explosive volcanic systems, you think?
Most of our rocks are intermediate, so
Okay.
anywhere from say 55 to maybe max 70. We do have some granites, but most of them are tonalites, quartz diorites, granodiorites. But that isn't to say, but again, these are kind of mid-crustal rocks. That isn't to say that there wouldn't have been more evolved, higher
Oh,
silica content rocks, higher in
right.
the crustal column, or I
Yeah.
don't know exactly what would have been exploding
Mm-hmm.
at the time.
Mm-hmm.
Um,
Fun
but
to
it's a
think
great
about.
question.
Yeah. Uh, I'm going to grab some more. Same thing. If you see something, go for it. Um, kind of ocean plate stuff. I don't know. That's kind of out of your. Well, Gary, are there any layered intrusives like the Stillwater in Montana in your complex? Or maybe he's thinking north where Pearson's working? Is that where the layered intrusives would be?
No layered intrusives where we are. In fact, most of our rocks are pretty massive and homogeneous, kind of like that picture of the Tiedemann Pluton that I showed you. There's not a lot of like short wavelength or small spatial scale heterogeneity, with the exception of something that we always just kind of garbage can called the diorite complex. So we do see, and we called it the complex because it was this really mingled zone, usually in the western part of the Coast Mountains, where the batholith tends to be a little more mafic. So I think I saw a question roll by in the chat about that,
Yeah.
like the Sierra Nevada, it does tend to be more mafic in the west, more felsic in the east, and that kind of goes hand in hand with that eastward migration, the younging to the east. But for the most part, no, not a lot of compositional complexity like what you'd have in the layered complexes that you mentioned.
Well, from your world, you don't see the Coast Mountains batholith as an easy extension or continuation of some other batholith further south, let's say. You don't see identical in peninsula ranges or Sierras, is what I'm hearing, or do you know enough about those other batholiths to make a connection like that?
On some level, I think they're all kind of the same. Like they're all Mesozoic continental arcs that developed above an east dipping subduction system.
Mm-hmm.
And so I guess at some scale, yeah, they are all kind of the same. I
Mm-hmm.
like to visualize a really large Pacific or Paleo Pacific plate to the west that wasn't a single plate. It was broken up and had different subplates. So there's going to be, of course, a lot of complexity from Alaska down to
Yeah.
Baja California. And if some of that complexity lives on. I mean, there's still like the Juan de Fuca still doing its subduction thing, whereas the rest of the margin has zippered up.
Yep.
But in that at that scale, the Coast Mountains is just one of these systems, and it just happens to be the largest currently exposed of all of those. So probably it was a bigger, more intact plate that was subducting in Mesozoic time to produce it. Um,
Yeah. Well, you can go so many directions and not have the expertise for all the directions. I think you said you did see some of the Carr and Siglock show, and obviously that's a whole other approach to this thing. So, yeah, I mean, everybody can contribute their expertise, and I don't know who the person is to put it all together. In fact, I get some emails from viewers saying I'm really having a hard time seeing how all this fits together, and I'm like, it's
they are not
okay.
alone. Yeah.
Nobody does. Nobody does. I
No,
mean,
no. And it's a lot easier. I mean, well, yeah, I don't, that's sometimes it's easier to, identify a problem, devise a series of experiments, write the proposal, and go and kind of tackle it in that area. But then once you kind of arrive at kind of a solution or interpretation of your data for that area, you then want to zoom back out and see how is that
right.
applicable regionally or globally, and
Yeah.
what are we learning about like the whole Earth system as a result of this study. And of course, that's where it gets very fuzzy because it's a really complicated planet.
It is.
Um, and it's hard to put all of that together. And there's only, maybe a handful of like kind of famous geologists that I think have done a really good job of writing these, more regional studies. Dickinson was one of them that could really see the huge picture.
Yep.
Most of us can't.
Right. Gary Paul asks, what is the depth of crystallization in your project area or areas?
Oh, great idea, or great question. It ranges. So the depths, I'm doing the mental calculation from the pressures.
Right.
So geologists estimate pressures using different mineral assemblages or different elements of minerals. And ours would be on the order of, say, maybe at the shallowest 10 kilometers deep to maybe 40 kilometers deep, something like that. And we think that when the Coast Mountain batholith was having its big flare-up events, that the crust was thickening. And so the crust might have been as thick as, say, 65 kilometers or so, maybe thicker, maybe 70 during some of like the really big flare-up events. So that'll give you some idea of like what segment of the crust we're getting a peek at here. That kind of middle zone.
And which generation is that when we have the thickening? Is that post or pre 100 million years ago?
We think we see it during all of the flare-ups. So one of the figures in the paper, my most recent paper that you shared with your audience, plots a number of different chemical indices against time. And you can see kind of like these jumps in the chemical indices, usually lanthanum, ytterbium, or strontium, yttrium. Those are just proxies. We're now using them as proxies for crustal thickness, which some people may challenge, but this is becoming a hot thing to do these days, I guess. Those proxies definitely work in the modern world. And so where we see higher strontium, yttrium, for example, we think the crust was thicker. And we see these increases in strontium, yttrium values in our plutons. We see them spike up every time we have a flare-up.
Every time?
Yes. And so that's part of why I conceived of the model that I did. So it has to fold together all of our observations, the thickening of the crust, the greater kind of heat from the magma, the greater volumes of magma being produced, and then also this inward creep, or this continentward, eastward migration of the arc. It kind of pushes eastward during each one of these episodes.
Okay, well, I'm gonna try something. It may be not the right way to go. I think this is not yours. This is Bob Hildebrand, I believe. Is that correct? But you've had something like that in your paper 10 years ago?
Yeah, it looks like a reworking of our figure to some degree. Yep.
All right. Am I hearing you correctly that when you started 10 years ago in the Coast Mountains batholith, you were thinking about crustal contamination, for lack of a better term, and you were more focused on how much is intermontane and how much is insular? And am I now hearing that more recently you're not as interested in the exotic terrain kind of basement of this story, and you're more interested in the external mantle generation of the story?
So where that figure was created is to the north, where we had just enough variability in our hafnium isotopes to start to make some guesses as to what may have underlain the batholith or been present prior to the intrusion of all these voluminous tooth-like, or they all look like molars to me. Even as I was drawing them in Illustrator, I thought, I'm drawing molars. So even then, we were trying to make our best guesses as to, so for example, Stachenia is young. So that green stuff off to the east, the blue stuff to the right-hand side to the east, that's Stachene and or Yukon Tanana. Yukon Tanana has rocks that are derived from the interior Laurentian North America, so they're very old. It has Precambrian detritus in it. If some of that stuff gets melted and incorporated into the little molars there, then it will become very apparent in the isotopic signature. We'll see that. And we thought we did see that. So that's why we drew a little sliver of Yukon Tanana in there, in with Stachene being folded in. And so we were taking our best guesses, not just based on the Pluton chemistry, but also on the metasedimentary country rocks that George Garrels had previously worked on. We had some other pieces of evidence to suggest, the batholith is not as volumetric at that latitude. So there are actually some scraps and pieces of the country rock that we could look at. So we put those together with the hafnium isotopes and kind of painted that picture. In the south, good luck finding a piece of metasedimentary rock. We sampled all we could. George and his student published it recently. It mostly looks like intermontane terrain, not insular, for what it's worth. It doesn't look like there's much insular in the, wait, am I saying that wrong? I believe I'm saying that wrong. I'm sorry.
More insular?
Anyway, and there's no evidence for any Yukon Tanana anywhere down there, but we're dealing with, slabs of rock that's maybe the size of the desk I'm sitting at in a sea of chronolite.
Everything got swallowed up. The whole scene just got invaded and incorporated. So how are you?
And the Plutons aren't helping us because they don't.
Right.
From what we can tell, they're not incorporating any crust. And if they are folding in any crust, then it doesn't look isotopically or geochemically very different from the mantle. It has to be something that's very young and itself was only extracted from the mantle geologically recently, like maybe Rangelia. Rangelia, has a lot of it is Mesozoic itself and is, mafic and oceanic in nature.
Man, loving this. Let's do 3 more. You probably got something else to do here. Let's wrap this up with you. 3 more. I'm down here live, viewers, I think. Regine from France. Are the magma fluxes fixed while North America was moving west above them?
So, good question. I'm trying to think about how to think about that. When we talk about the fluxes, we're really just talking about periods of time, but during those periods of time. So a flux period in the Coast Mountains might be anywhere from, say, 5 to 15, maybe even 20 million years long in duration.
Right.
And during those flare-up events, we actually see migration of the arc inboard or to the east in every case. And so I make a big deal in my paper about why those phenomena might be connected to one another, but I hadn't really thought about it before as being related to westward motion of North America, because that is really a slow creep that, as best as I know, is not changing through time, and certainly not at those time scales that we can resolve. So there's no reason to believe that the overall plate motion of North America is doing anything punctuated at the 5 to 15 million year time scales. So my hunch is that it's not related to that necessarily. So they're fixed in the sense that the arc is doing its own thing. North America might be kind of on the slow drift to the northwest, but really it's probably more of a subduction rate or subduction angle problem than it is anything to do with North America. We like to think of that as being the stable plate anyway.
Yeah. Doing great. 2 more.
Great question.
Yeah, it really is. Ian from Australia. What process initiates the vast uplift necessary to expose these plutons? So you're not exactly saying there's massive uplift in your field area. I think I heard you say that.
It's a super awesome question. It doesn't have a whole lot to do. So the process that creates, volumetrically big batches of magma may not have anything at all to do with the process that exhumes that frozen magma to the surface later. So we're talking about they're 2 totally different can of worms.
Yes. Right.
One is like the magmatic history. The other is, how is it that today we're walking around at, 20 kilometers below what was then the surface? And that probably has to do with a number of different things. It's a combination of exhumation that's occurring magmatically, because a lot of these big magmatic episodes are happening during contractional tectonic events that are associated with thrust faulting. So thrust faulting can do some of that exhumation for you. And then in the case of the Coast Mountains, we know that a lot of the exhumation is actually glacially driven. So is happening in the relatively recent geologic past,
Wow.
thanks to the glacial buzzsaw, if you will.
Yeah. Are there thrust faults mapped through some of your plutons?
Oh yeah, so the highest peak in the Coast Mountains is Mount Waddington. It's right smack in the middle of our most recent study area, and it's associated with the Mount Waddington fold thrust belt. So there's a big fold thrust belt that's exhumed there, but it's on the easternmost margin of the batholith and actually wraps up on country rocks to the batholith. So a lot of what's in that fold thrust belt is not the igneous rocks themselves, although there are meta igneous rocks certainly involved. And most of that deformation is Cretaceous. So there's a lot of good reason to believe that there's contractional deformation during at least one of the Cretaceous flare-up events. And in that case, the story seems to hang together really well. You've got contractional deformation, we've got garnet growth happening, we've got a big flare-up event, we've got thickening of the crust. It all kind of makes sense. The problem is that we don't see thrust faulting or evidence for contractional deformation during every one of these flare-up events. Sometimes we do, sometimes we don't. So it's very hard to construct a unified model that might be able to explain, each one of these events. Yeah. And so if you talk to some people, and maybe Basil would be one of them, he would say that's because you can't just come up with some recurring model that's going to explain 150 million years of arc history. Each one of these flare-ups is its own unique tectonomagmatic event, and that's how we should be thinking about it. So he could be right. Like maybe we're just putting up straw houses to be blown right down. I don't know.
Well, the flavor of this whole thing is it's just fun to hear from so many different kinds of folks and with all different levels of expertise, and we're all just trying to learn what we can. So the blowing over of straw houses, thankfully, is not happening anytime soon here, but it's a decent community. I think that's plenty. I know we got more questions. Viewers, I'm sorry we didn't get to all of your questions, but it's 3:30. I think we need to wrap up. Anything you wanted to finish with, Robinson? Any stray thought or a question that caught your eye, or should we say goodbye?
I don't think so, but I'll just say thank you, Nick. This was really fun. I had a great time doing this, and I was very nervous just at the size of your audience, but everybody was very kind, and it was fun keeping one ear on you and then one eye on the chat and seeing all the great community that you've built here. It's awesome.
Thank you.
So thank you.
Well, thank you. It was a real pleasure to meet you, and I hope we can do this again sometime, maybe next winter. Who knows?
Okay, keep me in the fold.
Sounds good. All right. Well, you have a good night, and thanks again for your time.
Thank you, Nick. Bye, everyone.
Bye-bye. Dr. Robinson Cecil, California State University, Northridge. I think that's in the San Fernando Valley of the greater Los Angeles, California area. What a treat to have her. I didn't know what to expect, and she sure was fun to listen to and interact with. Let me go down to live, or maybe even scroll back a little bit. We'll just put a little icing on the cake here. And it looks like many of you enjoyed Robinson's visit as well. Why wouldn't you? My God, she was just such a natural. You can tell who teaches, you can tell who has practice communicating this stuff. And of course, we could have gotten much deeper into the geochem, but I'm afraid of that stuff. So we probably didn't lean too hard into what her real strengths are, but she rolled with it beautifully. Who did the wonderful artwork? Oh, she was at home. She's got a couple of girls, I think. I'm scrolling way back, and why do I do this? I don't know. I think I know why. Precious metals, PD Riot wants to say. Right. W. Mann, would the Straight Creek Fault release compression and lead to extension? Any sense of depth of cooling for the non-volcanic rocks? Okay, so I think you know how these go lately. I get ramped up in my preamble thing, and then I see that I've already gone for half an hour, and I want to get to the guest. So I did have something else I wanted to do on the chalkboard, so let's do that before we quit. Yeah, here it is. I kept this from the well, you know what? Let me do this first. So I think, no, I know, I don't have to think. I know that you guys are very sharp. And in real time, you catch everything that our guest says. I know that. I can tell when I watch the replay, I can tell that you're right on the details of what our guest is saying. I'm kind of distracted by some of the other stuff I have to think about, but that's an excuse. I'm not as quick a thinker as you are. So I learned so much by watching the replays of these shows, and I can pause it and listen and think about what the guest was saying. So my point is, Robinson effortlessly started talking about these magmas, and part of me wants to recap what she said, but I can't do it. That's the point. I can't do it until I watch the replay 2 more times. So all I can do is try to grab onto what I thought I heard her say. I think she said didn't she? The Eocene magmas were the biggest flare-up out of the 4? And again, these 4 pulses of magma in the Coast Mountains batholith as a whole are generally working their way from the coast towards the inland. Now, why would the Eocene magmas be the biggest? That really surprised me. Now that I say that out loud, I remember Mike Eddy saying that these 2 guys were volumetrically huge in the North Cascades, and this was barely a flare-up, as Mike, I think, said. So I guess I'm backing off. I guess I'm not that surprised. If our Eocene Plutons are significant in the North Cascades, I'm going to think harder about how big is big for her biggest flare-ups in BC. I'm pretty sure that's what she said, but maybe I can do a little bit more with comparing sizes here. Why would that be helpful? Well, if they're comparable in size, then is that a continuation of our story? And if that's a continuation of our story, are we continuing our slab rollback thing? We're back to Jeff Tepper again. Come on now. And Jeff is kind of, in sync with Spencer Fuston's work. Wow. What did Spencer have? Okay, I didn't even think of that. Now, how much of this Eocene story is the direct result of what Spencer was finding with the Yukon slab, which brought back to the surface was the resurrection? Well, as Robinson says, how are you supposed to figure all this stuff out and keep it all straight? Even Karen Seglock said you can't keep it all straight, although she probably can. No, I wanted to get to the real thing, right. I'm energized. Thanks to you, thanks to our guest. We'll finish with, I didn't even redraw this. This is from the Idaho show. The look is the same, right? The look is the same as we've been doing for a solid month. Rangelia and friends, the insular superterrane, docks 100 million years ago, that's Basil's hit. Massive suture, that's Karen. Karen Seglock saying this was fixed and North America hit this with westward subduction. Now clearly, our guest today is an eastward subduction gal. She didn't go to Stanford, but essentially she was talking Stanford stuff there. Okay. She's the majority, remember? Going way back to our Rocky Mountain show. Flat slab subduction, that's the model that most tap into. But I'm showing this to you again simply to say, with our 4 batches of magma in today's topic, 2 of the batches, I forgot the dates, you got them, are older than 100 million years ago. We don't have anything older than 100 million years ago in the Idaho batholith or the North Cascades. Everything is younger. I'll add one caveat to that. In the last show, the Idaho batholith, I conveniently ignored a Pluton way north in Idaho. Did you catch it? Or do you have the Roadside Geology of Idaho book that I was recommending? I don't have it handy. There is an older than 100 million year old Pluton in northern Idaho, which I don't understand. So I'm addressing that as a fly in the ointment here. But for the most part, in the North Cascades and most of the Idaho batholith, everything's younger than 100, and we're back to that Cretaceous fireworks theme. But today, what were we? Back to 140 million years ago, with some significant magmatic flare-ups out at the coast. I will leave you with this. It's a radical departure from our guest. It's almost impolite for me to do it in a show with her because I thoroughly enjoyed her. But I'm going to do it anyway. Remember, our Coast Mountains batholith is straddling the boundary between the insular superterrane and the intermontane superterrane. And if we drink the Kool-Aid with Darrell Cowan, and we have much of this story being insular, and therefore we have pre-100 million year old Plutons invading insular, how are you going to do that if you have an eastward subducting Farallon plate through this whole story? So I think what I'm asking out loud is that I wonder how many of these older than 100 million year old Plutons that are currently in British Columbia were liquid and hot when they were out in the middle of the Pacific Ocean. With Karan and Mitch's fixed insular superterrane with a Mescalera ocean slab subducting westward out there in the water. I'm keeping that rolling around in the back of my mind. It's almost, I'll finish with this, it's almost like if we factor in the Karan-Siglock model, Karan and Mitch, if we factor in Baja BC, which we're saving until next winter, and if we factor in Jeff Tepper's slab break twice and roll back story, it's almost like our 4 batches of magmatic flare-ups in present-day British Columbia is like a combination of Oceania magmas, Mexican magmas, and homegrown British Columbia magmas. Welcome to the Lunatic Fringe, everybody. A toast to you. Here's to your health. Here's to your health. Thank you very much to Dr. Robinson Cecil for her expertise and her time. Thank you to you for staying with this program all the way to the end, for staying with this series. I don't check the videos every day. I never look at the analytics of who's watching where at what time and how many women over 60 and all that kind of stuff. All that data is there. I don't look at it on purpose. But I do notice occasionally that people are doing their homework and like, oh, I got a live stream coming up on Wednesday. We better watch that one that happened last Saturday. We better do our homework, in other words. I'm seeing that. I don't think that's imagined. I think that's real. So a special thank you to you for keeping up with the series, and especially if you want to watch something live and going back and making sure you watch the one that you missed. That's just kind of a fun thought of everybody scrambling to watch the previous letter before they watch one live. So I think I see you if you're doing that. So thank you for doing that. Last comment, then we'll quit. No, if I say it out loud, I'll ruin it. So I'm going to try to go to the iPad one more time, I think. I don't know why I feel like tempting fate. Put the order in for the new laptop on December 1st. Takes a while. No, we don't have it. I don't get it. Nope. I'll have to talk to Nat. I was simply just going to show you the calendar. So, when's the next time I see you? I think you know by now, right? We do these every Wednesday afternoon at 2 p.m. Pacific time, every Saturday morning at 9 a.m. Pacific time. And we're not in the North Cascades on Saturday. I've already explained why. We're going to Montana. And we will be looking at Plutons big and small in Montana that may or may not continue our understanding of what we learned in Idaho. Hell, I don't know, maybe what we learned today, maybe it won't help us at all before we go to the North Cascades with Stacia Gordon next Wednesday. But we'll see what we can learn from a former student who now is a well-respected igneous geologist in Montana. Thank you. I love you, and goodbye from Ellensburg, Washington, USA.